¿Qué tal? Muy buenas tardes tengan todos. Hoy tenemos nuestro coloquio del Instituto de Física de la UNAM, como sucede el primer jueves de cada mes. Y tenemos hoy el honor de tener al profesor Luis Santos de la Universidad de Hannover, de Leibniz Institute, ¿no? Bueno, Leibniz Universidad. No es el instituto, pero muy bien. Y está en el Instituto de Física Teórica. Entonces, nos va a hablar de gases dipolares, desde los supersólidos, ¿no? Hasta el desorden de localización libre, una cosa así, no sé, en la traducción, pero bueno, ahorita nos platicará un poco más. Pues muchísimas gracias por estar aquí. Profesor Santos y el doctor Romero, jefe del Departamento de Física Cuántica y Fotónica, pues va a hacer una breve introducción de su carrera y gracias por la charla que nos va a dar.
Pues muchas gracias, Cecilia, y muchas gracias al doctor Santos por estar aquí. Es un honor para mí presentarlo. Entonces, seré breve. Entonces, el profesor Luis Santos se licenció en la Universidad de Salamanca, en España, en 1995 y recibió su doctorado en 1998 con un trabajo sobre enfriamiento láser bajo la supervisión de Luis Rosso y Maciej Levenstein. De 99 a 2001, trabajó como postdoc en el grupo de Levenstein en la Universidad de Hannover, en Alemania, y en el 2001 recibió el premio Sofía Kovalevskaya de la Fundación Humboldt, que le permitió liderar su propio grupo en la Universidad de Hannover hasta 2004. De 2004 a 2006 fue profesor asociado en la Universidad de Stuttgart y desde 2006 es catedrático en la Universidad de Hannover. Y también desde el 2010 es el director del Instituto de Física Teórica en esa universidad. El profesor Santos ha publicado más de un centenar de artículos con más de 16,000 citas recibidas. Su foco de interés es la teoría de los gases ultrafríos, en particular condensados de Bose-Einstein y átomos en redes ópticas. Entre sus trabajos destacan la descripción teórica de la estabilidad y condensación de Bose-Einstein de gases dipolares, así como el estudio del carácter Roton-Maxon del espectro de excitación de gases dipolares y la emergencia de la fase supersólida, de la cual nos va a hablar el día de hoy. Muchos de los resultados de sus estudios se obtuvieron en estrecha colaboración con grupos experimentales europeos. Por otro lado, también parte de lo que nos hablará hoy, el profesor Luis Santos ha conducido estudios en la dinámica y localización en modelos de spin con interacciones de largo y corto alcance, en donde se destaca la descripción de la multifractalidad de las excitaciones de spin y el crecimiento algebraico universal de la entropía de entrelazamiento en sistemas localizados de muchos cuerpos con interacciones de ley de potencia. Así, de manera breve, podemos resumir que el profesor Santos es un experto mundial en gases dipolares, gases espinoriales, magnetismo sintético y la dinámica de sistemas cuánticos de muchos cuerpos en redes ópticas. Profesor Santos, muchísimas gracias por aceptar compartir con nosotros una parte de sus investigaciones en este coloquio del Instituto de Física. Bienvenido. Adelante, muchas gracias.
Muchas gracias. Muchas gracias por la introducción y muchas gracias por la invitación. Es un placer estar aquí, aunque sea online. Y bueno, hoy me gustaría contar algo sobre gases dipolares. Voy a hacer la charla en inglés, como ya he comentado antes, porque las transparencias están en inglés y si no va a ser un poco de lío. Bueno, so today I would like to tell you something about dipolar gases. And in particular about two different scenarios in which the physics of dipolar gases may be qualitatively considerably different, or very different actually, than the physics of non-dipolar systems. So hence the title, From Supersolids to Disorder-Free Localization. So the physics of ultra-cold gases is very much determined by the interactions. This is despite of the fact that these gases are extremely dilute, let's say 8 orders of magnitude or more less dense than water. But interactions play a very important role because of the very small energy associated with temperature that you have in the systems, which are at very, very low temperatures of the order of the microkelvin or lower. And typically the interactions that one considers in this system are short-range isotropic interactions. And so you have a central potential, and if you consider the scattering in the central potential using the partial wave, so the expansion, then you see that only the S-wave scattering contributes at very low temperatures due to the centrifugal barrier. And this means that the scattering, the interaction at these very low temperatures is given by a single number, which is the S-wave scattering length. As a result, you can substitute your potential, which may be complicated, by a very simple pseudo potential, which provides the same scattering length, which is this type of delta-like potential, with a coupling constant G, which is up to some constants here, the scattering length itself. So this is what I will call the contact or contact-like interactions in the rest of the talk. Then as I say, there is a new generation of experiments, which actually is not so new already. It's already several years in which since there have been experiments on that, which deals with particles which, in addition to this contact-like interaction, possess strong dipole-dipole interactions. This may be either magnetic dipole-dipole interactions or electric dipole-dipole interactions. But what is important is that these interactions are very different. They are anisotropic, yes, so they depend on the angle sustained by the vector joining the atoms and the dipole orientation, and they decay much slower. Actually, they decay like 1 over r to the power 3 instead of the typical 1 over r to the power 6 that you have in this other type of van der Waals-like interactions. This is the case of magnetic dipoles, like chromium, or in more recent experiments, argon and dysprosium. This is the case of Rydberg atoms, where you may have relatively large electric, pretty large electric dipole moments, actually. And this is the case also of polar molecules. Now, if we see in a chart, basically, the different systems, so to say, in this graph here, basically, you go from the bottom left to the top right here, you go to more and more dipolar systems. So typical experiments with alkalis are here, so they are very, very non-dipolar. But magnetic dipoles like chromium or dysprosium or erbium are around here. They are pretty dipolar. They are pretty strong dipoles. But really, really strong dipoles you have actually with molecules. And of course, Rydberg is out of the scale. But Rydberg is actually affected by very strong losses. Molecules have been very affected up to, I would say, very recently by inelastic processes, including exothermic chemical reactions and even more bizarre types of collisions. And this is actually the reasons why most of the experiments in the many-body context have been performed actually with magnetic dipoles. And actually, I will comment about several experiments with magnetic dipoles later on. If I have time, I will also comment something about molecules and about these new ideas about how to avoid these inelastic processes. So coming back to this slide, what is important actually, as I say, one of the most interesting things for the rest of the discussion is the fact that this interaction is not only anisotropic, but it's also partially repulsive and partially attractive, depending on how these dipoles are interacting with each other. And the fact that it's partially attractive means that these gases are dangerous against collapse, right? So they tend to be unstable, and this will play an important role right now in my discussion. So as I say, the presence of the dipole-dipole interactions changes qualitatively the rules of the game here, and most of the physics that I will discuss actually have to do with the interplay between these two types of interactions that I just discussed: the contact interaction given by the scattering length, and the dipole-dipole interaction given by the dipole moment in the square. So these are the two scenarios that I would like to discuss here. One has to do with weakly interacting systems, so dipolar condensates, and the other is related with atoms in polar particles in optical lattices. So let's go to this first scenario. So I would like to discuss here works which I've been doing with several people. In particular, as it was mentioned in the introduction, I have really the pleasure to collaborate with fantastic experimental groups. And here it was also the case. It was very nice collaboration, in particular with the group of Giovanni Modugno in Pisa, and very, very especially with the group of Francesca Ferlaino in Innsbruck. And several of the works that I will discuss are done in collaboration with these people, Elena, Tom, and Russell in Innsbruck, and Luis and our new PhD student Daniel in Hannover. So, as I say, the physics of dipolar systems, and very particular the physics of dipolar Bose-Einstein condensates, is very much given by the interplay between contact interactions and dipole-dipole interactions. And this is actually very well summarized in this equation, which is the equation that describes the evolution of the wave function of the condensate. This equation is a non-linear version of the Schrödinger equation. So you have here the kinetic energy, you have the trapping. Up to here is the Schrödinger equation, of course, but now you have here these terms here. N is the density, so it's psi absolute value in the square. And this means that this term is a nonlinear term, so it goes with psi to the power 3 here. This term is related with the on-site, the contact interactions that I was discussing before, this type of interaction. But then in addition, you have this term here, which is non-local. So this means that the wave function in the position R now depends on the density in the position R prime through this kernel, which is given by the dipole-dipole interactions. So this, in general, is the so-called non-local nonlinear Schrödinger equation, or in this context, the non-local Gross-Pitayevsky equation. And so this equation is the equation that describes in mean field the physics of condensates of dipoles at low temperature. And this equation actually predicts that this system is, as I say, very prone to collapse. This is very easy to understand if we see the structure of this equation, because even if this is positive, if this here is in average negative, what it means is that the system tends to reduce the energy by increasing density and therefore by collapsing. So in order to prevent this, yes, you will need to have that this has to compensate this tendency. So in particular, if you have a system in which your dipoles are oriented in average head with tail, like here, so in an elongated configuration, then the mean dipole-dipole interaction is attractive, so negative. So you need a sufficiently large scattering length such that you make your system stable, because otherwise it is unstable against collapse. The contrary, if the dipoles are side by side, so what you have in this type of pancake-like confinement, this means that the mean dipole-dipole interaction, so this term in here, is going to be repulsive. So this means that you need now a negative scattering length to drive the instability in the system. So this is why now the stability, and this is a very peculiar feature of dipolar systems, the stability and in general the whole physics of dipolar condensates depends very much on the container, depends very much on the geometry of the problem. Now, what happens if you take a system and now you quench the scattering length from a value in which it is stable to a value in which it is unstable? This is actually something that can be done relatively easy experimentally using something which is called a Feshbach resonance. So basically with a Feshbach resonance, you can change basically at will the value of the scattering length in the problem. Now, when this occurs, right, the mean field theory tells you that your system becomes unstable against collapse. And sure enough, when the group of Tillman-Fau did this already many years ago, they observed, and they did it with chromium atoms, they observed the collapse of the system. So basically, they observed that the system basically imploded and then exploded due to the, because basically when it implodes, right, density increases so much that the system starts to have the so-called three-body losses. So it starts to form molecules, it starts to form whatever, and it is basically destroyed. Now, the surprise, which was a very big surprise, actually came when this experiment was repeated several years later in 2015 already. by the same group, but with dysprosium, a different atom. Then in that case, what they found was something very different. Instead of observing a collapse or several collapses in the system, what they observed was the formation of droplets. So basically, they observed quite stable droplets living for hundreds of milliseconds, which is quite a long time. And in which basically the particles were basically forming, as I say, droplets similar to basically like ultra dilute liquid droplets. And it was later on actually shown as well in the case of erbium. The explanation of this came actually pretty quickly, and it is very much related to an idea which was proposed by Dima Petrov in a very different context in this absolutely fantastic paper that is cited over there. And it is surprisingly due to the effect of quantum fluctuations. When I say surprisingly, it's because typically in weakly interacting systems, like it is the case of Bose-Einstein condensate, the mean field energy is typically much larger than the effect of quantum fluctuations. These corrections, the correction of the ground state energy to quantum fluctuations, the so-called Lee, Wang, and Yang correction, which was calculated already in the 50s, it is very, very small. It typically plays absolutely no role in the physics. Now, the question is that in the case of a dipolar system, the mean field energy is the result of two interactions which actually may compete with each other, the contact interaction and the dipolar interaction. And these two may compensate each other such that the mean field energy is very small. Now, this is a very important ingredient because this means that now quantum fluctuations could play indeed an important role. But they do play an even more important role because of the different scaling that they have with respect to the density. The density dependence of the mean field energy is mean field energy density, let's say, is n squared, whereas the mean field energy, the quantum fluctuation energy density goes with n to the power 5/2. So this means that if this mean field energy that is here is very small but attractive, now your system will tend to collapse, right? But then the density, the dependence of this is faster. And then this term will eventually take over because it grows faster. And the crucial point is that these quantum fluctuations are repulsive. So this means that this attractive dependence here may be compensated for a critical density by this repulsion here. So you have an attraction, you have a repulsion due to quantum fluctuation, similar to a sort of Casimir pressure in the system. And this stabilizes the system and forms a droplet. So this is a quite surprising effect due to quantum fluctuations, very unexpected. In the case of dipoles, actually, quantum fluctuations have exactly the same density dependence. This was calculated by Aristide Lehmann and Axel Pester several years ago than in the case of non-dipolar systems. Now, this is very well recovered by an extended version of this Gross-Pitayevsky equation that I was showing to you before, which is basically the working horse of most of the calculations that I will show you later, which contains, as I say, both the mean field energy, basically this part was the part that I discussed before, and then it contains a term here which introduces in local density approximation the effect of quantum fluctuations in the system. This equation explains this type of observations that were done in the experiment of Tillman-Fao, actually to a very good extent, definitely qualitatively, but also to a large extent quantitatively. But it predicts other things. It predicts, for example, that due to this effect, these droplets may be self-bound. So this means that you don't need a container actually to keep them together. So it really behaves like a droplet. Of course, you need to have something such that it does not fall in gravity in the experiment. But apart from that, you don't need actually a container. This is very different than the usual condensates, but you need actually a container. You need a trap. But an interesting feature of these self-bound droplets is that when you put more particles in your system, in a typical condensate, if you put more particles in the system, you increase the density. Here, the density is to a very large extent given by this equilibration between the two types, the quantum fluctuations and the mean field term. And as a result of that, instead of increasing the density, when you put more particles, you just make your system bigger, actually more and more elongated. And this has an interesting consequence, because if now you put a confinement along the direction of this of the filaments, right, of these droplets, this means that when you put more particles, at some point it's energetically very costly because you are gaining trap energy quickly. And as a matter of fact, what happens is that the system prefers to form more than one droplet, yes, because basically you are frustrating this growth. And then these droplets now see each other due to the dipole-dipole interaction, which is non-local. And as a result of that, as a result of this confinement, the droplets form an array, yes, from an order array. Another interesting point is whether these islands, which you are generating, are really isolated islands, or they are still talking with each other. There is a sort of phase link between them. And this brings me now to the discussion about supersolidity. Yes, because a supersolid is a system which combines two apparently contrary properties, superfluidity and crystalline order. This is a phase which was proposed many, many years ago in the beginning of the 70s and of the 60s. And actually it has been searched in helium, but its experimental realization in helium remains to this date elusive. It has attracted a lot of interest also recently in the field of ultra-cold systems. There have been experiments on supersolid or supersolid-like systems in cavities or with spin orbit coupled Bose-Einstein condensates. Also in these experiments, the periodic modulation of the system is actually to a very large extent externally imposed. In the case of dipolar systems, the first experiment which actually showed the supersolidity was this experiment of the group of Giovanni. And in this experiment, what they show, actually, this was in collaboration with our group, is that if you have an elongated system where your dipoles are actually, you compress strongly in the direction of the dipole, right? Then what happens is that the spectrum of excitations, and this is related with something that was mentioned in the introduction, the spectrum of excitations of a dipolar gas may present actually a minimum, which resembles the roton in helium. And when this minimum, actually the depth of this minimum depends on the scattering length. So if now you change the value of the scattering length, this minimum may eventually touch zero. And when this occurs, the system develops an instability with this momentum. And this modulation actually eventually triggers the formation of this droplet array that I was telling to you before. So what was done in this experiment was to quench the scattering length. If you quench to a value at which the roton is still not touching zero, you still remain in the unmodulated regime. If you quench too far, yes, then you form islands which are completely separated from each other. But if you quench in a narrow value of scattering length, you actually get an intermediate situation in which the droplets are still phase linked with each other, which is this super solid regime that I was telling to you before. So basically, the cooking recipe to create a dipolar supersolid is to combine dipolar and contact interactions with quantum fluctuations, with confinement, and fine-tuning of the scattering length. Right. So this is basically what has been done in all the experiments that I will show to you in a second. Because this has been, similar results were obtained very quickly after that by in Stuttgart in the group of Tillman, Fau, and in Nervion in the group of Francesca Ferlaino. And there have been a lot of studies which are discussed in this excellent review of Tillman, Fau on the excitation spectrum, for example, and other things. Also interesting to mention is that there is an alternative way of creating the supersolid, which is by evaporatively cooling into the supersolid, and this has been pioneered by the group of Francesca Ferlaino. Up to very recently, the supersolid array was just one-dimensional. So basically, you just have a one-dimensional set of droplets. But this has recently changed. And basically, the easy way of changing this is basically to relax the confinement in this direction, right? So the direction which goes out of the plane here of the slides is the dipole direction. This I would like to keep strong, but I can relax these confinements. And when I do that, I get a structural instability which resembles very much the structural instability that one has in trap ions, where you may go from a linear configuration to a zigzag configuration and eventually to with more and more arrays and getting into a two-dimensional configuration. The situation is, however, rather different in the case of droplets compared to the case of ions, because the droplets have an internal structure. And also that the number of droplets, contrary to the number of ions, which has to be conserved in this process, the number of droplets is not necessarily a conserved quantity here. So we have studied this recently with the group of Francesca Ferlaino by means of this extended Grosbeck equation that I was mentioning before, and some also variational methods. And indeed, we have been able to map the transition between one-dimensional and two-dimensional as a function of the trap aspect ratio and the atom number. So basically, as I mentioned before, when you have these structural transitions, you may also change the number of droplets and go from, I don't know, from 5 to 6, from 6 to 7, and things like this in typical experiments. So actually, these are the results of the experiments, which match very, very well with our numerics. And actually, in these experiments, they have shown that they are indeed dealing with a phase coherent system. There is alternative routes to produce these two-dimensional systems, which have been recently explored in Stuttgart. Now, you can go to even more two-dimensional systems, having more and more rows. But if you try to do it in a trivial way, which is just opening your transversal trap more and more and more, this can work for ions, but it does not work for droplets. As I told you before, the droplets have an internal life. And if you reduce the density too much, which is what you will do if you open your system more and more and more, then the droplets are simply destroyed. They are not self-bound anymore, and then you lose the droplet feature and therefore the super solidity. So in order to keep this, you need to fix the density. So when you open the trap, you have to increase the number of particles. And then when you do that, you may indeed get now a nice super solid in 2 dimensions. These are actually numerical simulations. Right? These are not experiments. I will show you in a second experiment. So another important question is which one of these two methods that I was telling to you before for the creation of the super solid is better, quenching versus evaporative cooling. This is something that we studied in this recent work. And it is indeed the case that evaporative cooling is much better for producing quickly a good super solid with a good phase coherence. So I'm actually using these ideas, the experiment of Francesca, they have been able to generate this type of super solid, which is this one in the numerics, right? Which is going more and more into this idea of going into 2 dimensions. Actually, there is a lot of possibilities for 2-dimensional super solids. For example, there are also a lot of open questions about the issue of superfluidity itself, not just phase coherence. For example, whether one could observe vortices, for example, and things like that in these systems. This is still a pretty open question. So another possibility is that actually you may get different types of pattern formation in this system. I will not comment much on that. But there have been very nice studies of the group of Thomas Paul and the group of Tillman-Fao on this issue. So the final thing that I would like to mention about dipolar condensates is also a recent development, experimental development in Innsbruck, which is the fact that one is now able to trap and condense different types of dipolar systems. So they may be atoms in the same with the same isotope at different electronic states, for example, or different hyperfine states. They may be 2 different dispersions or Erwin dispersions. You may have these mixtures. The physics of mixtures has attracted a lot of interest in the community of ultra-cold gases from its beginnings, right? For example, whether these components are miscible or immiscible, for example, it attracted a lot of interest several years ago. So, but one of the interesting things that you have with mixtures, starting with non-dipolar mixtures, is the fact that non-dipolar mixtures actually offer another different scenario for the creation of quantum droplets. And this is actually the scenario that was discussed originally by this paper that I was mentioning to you before, this fantastic paper of Dima Petrov. So basically, if you have a non-dipolar mixture with two components, 1 and 2, you may have interactions blue-blue and red-red, I call intra-species interactions, and blue-red interactions. Now, if the intra-species interactions are repulsive, but the interspecies interactions are attractive, then you have something similar to what I discussed before. You have two competing interactions. Before it was the contact interaction and the dipolar interaction. Now all these are contact interactions, but one are interspecies and the other is interspecies. Two of them are repulsive and this one is attractive. So this means that you can actually quasi-compensate them, quasi-cancel them, and therefore get a very small mean field, which now compares with the quantum fluctuations, and you have, again, the same mechanism of quantum stabilization if these mean field interactions are slightly negative. So you get quantum stabilization against collapse, and this has actually been observed in experiments in Barcelona in the group of Leticia Tarruel in IFUNAM, and in Florence, in Lens, in two groups, in the group of Marco Fattori and the group of Chiara Ford. So they have observed also the formation of these self-bound droplets. But these self-bound droplets demand actually the fact that these two components have to be miscible. And not only miscible, they have to be miscible with a particular density dependence between the two. Yes, the so-called polarization of the mixture has to be fixed, and fixed by the ratio of the scattering lengths between the two components. And this means that the droplets behave to a very large extent like a fixed single component BEC. So in reality, somehow this spin character is somehow lost in this. The situation is very different in the case of mixtures of dipoles. Yes, and this is something that we studied now recently in this paper. Basically, the equation that describes this is a sort of extension of this extended Gross-Pitagoric equation, but now it's a set of two, right, with a properly calculated Lewin-Yang correction. And these mixtures have actually a lot of physics, and still there is a lot of physics which is still to be studied, and we are studying now. And one of them is actually, without entering into all the details, is the possibility that you can have droplets of components which are not miscible. Yes, so you may have actually the situation in which you have two components which are immiscible, but still they form a self-bound droplet altogether. And the reason for this is because if you consider now, for example, the red droplet here, let's say that this is the red droplet. The red droplet, a droplet of one component, creates pockets of energy minima here at its sides, where you can now put the second component. And this actually acts as an attachment, as a glue between components, which allows actually to form these types of immiscible droplets. So another interesting thing that happens in dipolar mixtures is that the formation of droplets may depend extremely sensitively of the doping of one component by the other. So let me explain what I mean. Suppose that I give you a component 1, and this is alone, no? And now they form an unmodulated system. So here I don't have any droplet. Yes, so this is a regular condensate without any modulation, without any droplet or whatever. And now I start doping this system with the second component. Now what happens, very strikingly, so to say, is that under proper conditions, even a very small doping can induce, so this is component 1 and this is component 2, you start doping it, and eventually for a critical doping, you start creating this type of modulated system. Basically, you create a supersolid of droplets. And actually, it's a double supersolid because both components are overlapping and both components are supersolid. And this, as I say, occurs even for a very tiny doping. And actually, we have a good way of understanding this. Basically, the second component modifies effectively the interactions in the system, and actually makes the system significantly more dipolar. So we have a theory on that, but I will skip it here. So, so as a summary of this first part, we have seen that that there is a lot of very rich physics of supersolid and supersolid arrays. Basically, we have these droplets which are formed by quantum stabilization, and they may form these coherent arrays. There is a lot of physics to be explored in two-dimensional supersolids like pattern formation, vortices, and of course, there's a lot of physics also in dipolar mixtures. And some actually of them, like this work on domain supersolids, I did not have time to discuss. Okay, so this is the first part of the talk. Now I will switch to a rather different environment. So there's a rather different scenario. But in this scenario, also the physics of dipolar of the dipole-dipole interactions, the dipole interactions play a very, very, very important role and change very much the physics of the system. This is the case of polar lattice gases. This has been a work that we have been doing with several people here in Hannover. And also, I will not have time to discuss the work we did with the Guidos, Guido Pupilo, Guido Masella, and now there's also a recent work with Kuba Zakrzewski, and I would like also to mention Pinic and Luca. Okay, so the idea is the following. You can create a periodic potential for atoms in a relatively simple way, which is basically to interfere lasers such that you create a standing wave. And this standing wave, due to the so-called dipole force, induces a potential to sufficiently cold atoms. So this is what is called an optical lattice. If this optical lattice is sufficiently deep, then you can project the physics into just the lowest band of this lattice. You can, because you assume that the first gap is enormously large compared to any other energy scale in the problem. And then the problem becomes a tight binding problem, which is described by a Haber model. Now, in the Haber model, in the typical Haber model, you have hopping to the nearest neighbors, right? Which in one dimension is just to the right or to the left, but in higher dimensions, it depends on your coordination number. You have on-site interactions, right? So this is the typical ingredients of the Haber model. But in these models, like the model that you will have with polar lattice gas, you have in addition intersite interactions, which in the case of a polar gas, decay with 1 over r to the power 3. Actually, I will mention at the very end that this is not, strictly speaking, what is going to happen in experiments, like 1 over r to the power 3. This is true for point dipoles, but it's not generally true. But I will mention this at the end. The ground state physics of these systems with extended interactions is pretty well known. There is much more than just the usual multi-insulator and superfluid transition and superfluid phases that you have in the usual Bose-Haber model. You have different types of crystals, lattice supersolids, Haldane insulator phase, so for interlayer supersolids, interlayer superfluids, and so on. You have a lot of physics there. The experimental situation is much more modest, yes, despite of the breakthrough experiments of Francesca Ferlaino in Innsbruck on the extended Bose-Haber model in Synergion atoms, where the relation between this number, which characterize the intersite interaction, and this number, which characterize the hopping, is of the order of 2 or 3, and this ratio actually will play an important role in the discussion right now. But that's it, basically, for the moment with magnetic atoms, yes. But actually, what I was mentioning at the beginning, that there are interesting what is called shielding experiments against inelastic collisions in polar molecules, and these developments open a lot of interesting possibilities, not only for a BEC of polar molecules, but also for the study of Haber models with polar molecules, models in which the molecules can really move. Yes. Also, another type of systems you can simulate with dipolar systems are spin models. So there have been quite a lot of experiments on that. And this may be very interesting because spin excitations actually propagate with a power, with a 1 over r to the power 3. So it's very similar to have hopping with a power law, which is a topic that I know that, for example, in Mexico, you have been studying. And but I will not mention anything about the spin models. Yes, this is actually some work that we did as well, but I will concentrate just in the physics of this type of Haber models. And actually, we'll simplify the discussion and consider the so-called hardcore system, where the occupation can be just 0 or 1. So this is true if your on-site interaction is sufficiently strong. Now, which kind of physics you can have here? One of the interesting physics that you can have here is the so-called dynamically bound intersite dimers. So the idea is very simple. Suppose that for whatever the reason, I have two particles which are living in close neighbors. Now, if now I try to break this pair by putting this particle here by a hop, now I will have to release all the energy associated with this pair, which is actually V. Now, if this V is very large compared to the hop in energy, this means that this energy of the binding, which I have to accommodate in the band energy, I cannot accommodate it in the band energy. It lives basically in the gap, and therefore this breaking is forbidden. Yes, this is the idea of this dynamically bound pairs. I can still move in second order, so I move first one and then the other, and this leads to an effective dimer hopping, which goes roughly speaking like T squared over V. This is very similar to what happens with the idea of the so-called repulsively bound pairs. So basically, in on-site interacting systems, so with the usual Bose-Haber systems, if the on-site interaction is sufficiently strong for the same reason, now this cannot break, and this has to move also as a whole with T squared over E. But the difference between these dimers and these dimers is actually the fact that whereas here you just get a slowdown, right? In here, you get an additional small energy scale which may compete with this motion, which is the dipolar tail itself. So the fact that you have a dipolar tail, a dipolar intersite interaction. And this is very clearly seen if you consider the problem of two dimers. You consider two dimers at the distance L sides, yes? They are interacting with each other. So if now I move this dimer, let's say to the right or to the left, I am changing the interaction energy. If the change of the interaction energy between these two dimers now is large compared to the motion of the dimer, not to the motion of the particle, but to the motion of the dimer, which is much slower, then this motion will not occur, and these two will remain at a fixed distance, basically localized at this fixed distance. They will form a cluster of dimers, or a dimer of dimers. So now you can solve this four-body problem here and see that for a sufficiently large ratio of V over T, if these two are initially separated by a given critical distance, right? If the distance is smaller than this critical distance, they will remain bound. And in the moment in which you start to form these clusters, basically, you get a quasi-localization in the dimer gas due to this cluster formation, because these objects are, of course, extremely heavy, and they will basically localize. Another important difference of dimers in polar systems and is very much what happens in two dimensions. If I give you an on-site pair in a two-dimensional lattice, it will move in exactly the same lattice as the usual particles. It will move more slowly, but it will move in the same lattice. In the case of a pair, of a nearest neighbor pair like this one, this is not true. The dimer lattice is in general not the same as the particle lattice. This has been pointed out in this very nice paper of Nathan Goldman's group. And this has important consequences, in particular for some particular lattices. Let's consider a triangular lattice, this type of equilateral triangles here. And the dipole is perpendicular to the plane. So this means that this interaction between this and this is the same as between this and this, between this and this, and so on. So now, in principle, this dimer, the dimer lattice, which is these circles, right? Now this particle can move into here. And this means that now you move the dimer from this link to that link. Or I can move from here to here, right? And now I will change from other link to other link. So if now you make a plot of the positions that the center of mass of the dimer can follow, then you get this square lattice, these square sides here. And these square sides are not arranged in a triangular lattice. They are arranged in a different type of geometry, which is the so-called Cadmium lattice. The Cadmium lattice is characterized by appearance of a flat band. And indeed, if you solve the two-body problem here, in addition to scattering states, here you get the appearance of three bound pair states, which are these repulsive bound pairs. And sure enough, you get this type of flat band. It's not completely flat because of higher order processes, which are indicated here, but it's very, very flat. As a matter of fact, then, if you start with a dimer which is pretty localized, this dimer will now project into these bands, and partially will project also in this upper band. And as a result, the expansion is by model. You get something which propagates relatively fast with a velocity proportional to the hopping, and something which propagates very, very slowly with a velocity proportional to the t square over b. And flat band dimers actually lead to long memory of initial conditions, so it leads basically to quasi-localization. Another point which is interesting is that nearest neighbor dimers of bosons and fermions don't behave in the same way. Yes, this is pretty different than in the case of on-site case. Another important thing that I would like to mention is that it is not the case that you need a very large value of V over T in order to see localization effects. For example, it depends on your initial state, right? For example, if you start with a state which is, for example, all sites occupied, and you just remove the end caps and let it expand, then if the ratio V over T is sufficiently large, this will not expand, will remain self-bound. It will form a sort of lattice droplet, which should not be confused with the droplets that I was mentioned before, which is self-bound, but also self-pinned. It cannot move. It is just self-trapped in there. Here, this number is pretty interesting because it is already the case that one can reach these values in experiments. So we have seen that we can have particular conditions, like, for example, a dimer gas or this type of lattice droplets, in which I can get localization even in absence of any disorder. But the question is how general this is. So if I give you any initial distribution of dipoles in a lattice, how localized it's going to be in absence of disorder, right? And for this, I would like to introduce the idea of Hilbert space fragmentation, which is an idea which has been put forward recently in the context of precisely of the study of localization in absence of disorder. So, and for this, we need to understand the difference between a model with just nearest neighbors and a model with this dipolar tail, because this difference is pretty important, in particular, the V over T is sufficiently large, but not only, as I will show you later. So this is a model. In principle, I can have also disorder, but this will not play such an important role in the discussion. I have hopping and I have nearest neighbors, purely nearest neighbor interaction. Now, if this ratio V over T is sufficiently large, right, I have an emerging dynamical constraint in the system, which is that I have to conserve this number of here. Yes, this number is very strong because this is this number is very robust, so to say, because this V is pretty large. And actually, this is just another way of seeing now in a many-body perspective this idea of the dimers that I was telling to you before. Now, what this means is that now I split my Hilbert space into different regions, which are characterized by this quantum number, which is given by this emerging dynamical constraint. But this is even more important because now there are many states which have this the same number of nearest neighbors, but which cannot be connected by the dynamics with each other. Yes. And this means that now the Hilbert space is going to be even more fragmented, right? So I have fragments of my, in principle, I fragment even these blocks. So the states which can't really connect with each other are very, very limited. Now, in the case of nearest neighbor interactions, in principle, if the number of singlons, I mean particles which are not paired, is sufficiently large, despite of this fragmentation, you may have actually an effective delocalization in the system. So this is actually due to the following simple idea. If I have a single particle, yes, which comes to this distance of a cluster, yes, this cluster alone cannot move if V is very large, supported V is infinity. This cluster alone cannot break, it cannot move, basically. But if I put a particle here, now this particle can move here, and this keeps the number of nearest neighbors fixed. Now this will jump here, this will jump here, and eventually, as a result of this, I will end with my clustering here and my synchrone moving to the other direction. So now I swap the positions of the two, and every time a synchrone goes by, a cluster gets a recoil. So I get a sort of Brownian motion, and as a result of that, I may eventually delocalize clusters of any length. The situation is very different if you have a 1 over r to the power 3 interaction, or you have a tail actually. And the reason is because when in the nearest neighbor model you increase V, you are just enforcing more and more and more this constraint. But when you increase V here, you are not only enforcing more and more that constraint, but you are creating new constraints like the conservation, for example, of next to nearest neighbors. And this is enough, actually, at half-filling in particular, to shatter the Hilbert space. So basically, now where you had blocks of states which could connect with each other, now these blocks are smashed, are basically reduced to mini blocks, right? And actually, this number of here, which I will not have to discuss, time to discuss, basically, if V over T is of the order of 20, this number basically indicates this breaking of the pairs. Basically, it's telling to you that it breaks exponentially these pairs. These blocks. Okay. Now, moreover, if you study the motion of the particles now in these mini blocks that you can really move, now you see that these resonance swaps that I was discussing to you are prevented because now the particles, due to the conservation of next to nearest neighbors, cannot approach to the nearest neighbor. Yes. So now this kind of process is stopped before it occurs. So there is no swapping, and the dipolar tail will for sure now favor a strong localization in the system. And indeed, this is what happens. You can start, for example, with some state which you have a cluster and you have synchrons here. With the nearest neighbors, basically they delocalize. I don't have time to discuss this, but basically with the nearest neighbors, they delocalize, and with the tail of the dipolar interaction, they strongly localize. Now, an important feature, which, and now this is the last thing that I would like to discuss, is that this mechanism that I was telling to you of resonance swapping is only efficient if the number of synchrons is sufficiently large. So if the number of these not pair particles is sufficiently large, because otherwise, if this is not the case and I don't have enough synchrons, this means that these clusters will not have too many recoils, right? Yes, in closed systems, so not in periodic systems, but really in real systems, closed systems, and this means that even in the nearest neighbor model, I will have a large residual inhomogeneity of my system. So what I mean with this is that I start, let's say, with a given Fock state distribution, which is very inhomogeneous, and I wait for a sufficiently long time and I see whether the density has become homogeneous. So whether my system has become, let's say, if you want, ergodic. And the answer in finite systems is that this is very far away from being the case even in the nearest neighbor model. So basically, this is this inhomogeneity, so to say. 1 means very inhomogeneous, so the initial state. 0 means very homogeneous. And this is basically the inhomogeneity evaluated for many different types of initial states, which just fulfill a given number of particles on a given of nearest neighbor. And you see that that also the nearest neighbor model has a relatively large inhomogeneity even for a very, very long time scale, right? So this is basically localized. But the dipole has a much larger localization. So the inhomogeneity is much stronger in the case of dipole. And this is an average over many initial states, not just particular states. Now, an interesting surprise is that if now you see what happens for, not for a large dipolar interaction, but for a much modest interaction, then you see that the dipole actually helps to delocalize rather than to localize. Yes, the reason for this is actually related to basically, which is the energy penalty that you have when you break clusters. And now, and this is the very last thing that I would like to well, this is basically this summary that I was making. So basically, when V over T is sufficiently large, you go from 1 over R cube induced delocalization to 1 over R cube induced localization. And now the final thing that I would like to mention, and this is the thing which we are now currently investigating, is what happens in a real polar lattice system, not in a theoretical polar lattice system. So what happens in a real polar lattice system? In a real polar lattice system, you don't have this type of point-like interaction 1 over s to the power 3. This interaction coupling constants that you have in the Haber model are this type of terms here, which depend on how the so-called Barnier functions look like in the site. So basically, this is the wave function of an atom inside of a site, which you can understand as a sort of like Gaussian-like cloud here. And this is not a point. It has a given size. And in particular, if this size now is comparable to the, in particular, the transversal size is comparable to the intersite spacing, now this interaction does not behave in this way, but it behaves rather more like that, right? With some constant here, which depends on this geometry. And as a result of that, this means that in particular, the ratio between nearest neighbor and next to nearest neighbor interactions, which is crucial for the shattering that I was discussing with you before, will depend on the geometry. And actually, indeed, you can repeat the same calculations, but now with different geometries. This is the 1 over r to the power 3. And this is a different dependence. In particular, the ratio now, instead of being 1 over 8, is 1 over 3. And you see that sure enough, now you get this strong induced localization. So basically, the inhomogeneity in a very long time is much larger in the case of these systems than in the case of the nearest neighbor, and even than in the case of 1 over r to the power 3. Yes. So basically, you enhance localization. So with this, I would like to finish. So with polar lattice gases, we have seen that you can have a lot of very interesting dynamics of dynamically bound nearest neighbor dimers. We have seen that you can get localization due to dimer clusterization, in which you enhance the role of the tail of the dipolar interaction. You can localize via flat band dimers. You can have self-bound and self-pinned lattice droplets, Hilbert space shattering due to emerging constraints. And in addition, you can have this localizing, delocalizing role of the dipolar tail, and also this important effect associated with the geometry of the Barnier function. So with this, I would like to finish, and thank you very much.
Muchas gracias, profesor Santos. Le damos un aplauso a distancia.
Gracias.
Gracias, muy interesante toda la charla. Me gustaría pues invitar a los colegas a que tengan una pregunta. Me decía el profesor que lo pueden hacer en inglés o en español, como gusten. Y también me imagino que lo puede contestar en inglés o en español, como sienta más cómodo.
Sí, yo las preguntas y las respuestas pueden ser en español.
Ok. ¿Está Cecilia? ¿Es una pregunta?
Sí, gracias. Gracias por el coloquio. Felicidades. Yo tengo una pregunta. Al principio en estos gases dipolares, ¿no? Dijiste que necesitabas que eran demasiado diluidos, ¿no? Comparados con el agua. Y cuando se van formando los supersólidos,
Sí.
¿qué tanto es diluido? ¿Y qué tanto entonces hay la interacción dipolo-dipolo en estos sistemas diluidos? Y bueno, se está considerando un campo medio, entonces pues no hay interacción de pares o de tres, etcétera, ¿no? Entonces, ¿qué tanto en los experimentos, ¿no? Este tipo de aproximaciones son válidas? ¿Cuál es la validez de todas estas aproximaciones? No sé si son muchas preguntas, pero...
No, está bien, y además es una muy buena pregunta, porque de hecho esto explica lo que, como he comentado al principio, en los primeros experimentos que se hicieron al llevar el sistema a la situación inestable, en vez de observar las droplets, observaron el colapso del sistema. Esto es porque en el átomo en el que lo hicieron, que es Chromium, lo que ocurre es que este mecanismo está presente también. El problema es que la densidad que uno necesita para que se compense mean field fluctuations con quantum fluctuations es una densidad tan grande que antes de que eso ocurra en experimentos, lo que ocurre es que el sistema desarrolla lo que se llama free body losses. Las pérdidas a 3 cuerpos implican que lo que tienes es una interacción a 3 cuerpos, ya no es una interacción a 2 cuerpos, porque ahora la densidad es muy grande, precisamente esto. Y lo que ocurre es que en esta interacción a 3 cuerpos, 2 de ellos forman una molécula y el tercero se lleva la energía. Y el resultado, la energía es sobrante, porque la molécula tiene una energía negativa, digamos, está atrapada, está bound. Y entonces lo que ocurre es que los 3 se pierden, ¿no? Entonces, este mecanismo es el mecanismo fundamental que determina la vida media de estos experimentos a una densidad lo suficientemente grande, que es, digamos, en todo experimento de condensado lo suficientemente denso. Es esta física a 3 cuerpos la física que determina. Y como digo, antes de que el sistema pudiese desarrollar interacciones a más cuerpos, digamos, el sistema explota, ¿no? Y de hecho, en las droplets, dependiendo de qué sistema, lo que ocurre es que en dysprosium, por ejemplo, la densidad necesaria para que se estabilice la atracción de min-field y las fluctuaciones cuánticas es lo suficientemente pequeña como para que la interacción a 3 cuerpos sea importante, pero no sea catastróficamente importante. O sea, uno puede llegar a ver droplets, pero que como la densidad es grande, las pérdidas a 3 cuerpos son relativamente grandes y en un tiempo más pequeño del que suele ser el caso en experimentos de condensado, el sistema sencillamente pierde demasiadas partículas. O sea, la densidad, de hecho, es grande, pero en este tipo de líquidos, digamos, es como si fuera un líquido, porque es una droplet, la densidad no es brutalmente grande, digamos.
Las fluctuaciones cuánticas se promedian, supongo que en el tiempo en que se observa los gases o no, ¿no? O sea, supongo que son demasiado rápidas o no.
Sí, de hecho,
comparado con los tiempos experimentales, ¿no?
El modelo que describe esto es un modelo que está basado en el cálculo homogéneo, digamos, de la energía del ground state, ¿vale? O sea, tú estás asumiendo que el sistema equilibra localmente, digamos, rápido. Eso es verdad. Y entonces, lo que sucede es que esta ecuación, que como digo, es una ecuación que utiliza, de hecho, también ideas de local density approximation y otro tipo de cosas, es una ecuación aproximada cuya validez es mucho menor que la validez de la ecuación de Grosseteste normal, digamos, pero que funciona muy bien para los experimentos. Sin embargo, hay experimentos en los cuales se ha visto que tiene una discrepancia cuantitativa importante. Okay. Y eso es porque esta ecuación tiene una serie de aproximaciones y, digamos, uno trabaja en el régimen en el cual la aproximación no es mala, pero no es perfecta. Eso es seguro. Y no se sabe muy bien, de hecho, por qué ciertos experimentos, digamos, todos los experimentos se describen cualitativamente hablando muy bien con este tipo de ecuación. Cuantitativamente hablando también, pero hay ciertos experimentos en particular, por ejemplo, los experimentos en IFO o algunos experimentos en Stuttgart, que han mostrado discrepancias. Entonces, la gente ha hecho Quantum Monte Carlo, por ejemplo, para estudiar esto, que casa bastante bien también con los resultados de la Extended Grosseteste. Y luego hay ciertos cálculos de Quantum Monte Carlo que tampoco casan tan bien con los experimentos. Digamos, hay un cierto trabajo por hacer, yo diría. Pero digamos, la ventaja que tiene estos modelos, o esta Extended Grosseteste, es que provee de una imagen clara y simple de la física, al menos cualitativa, del problema, que probablemente con otros métodos más complicados, más exactos, probablemente se perdería. También es cierto.
Okay, gracias. Es que aquí tenemos al experto en dipolos, ¿no? Aquí está, güey. Pero gracias.
Había visto por ahí una mano levantada, parece que ya no. Bueno, entonces en lo que alguien más se anima, yo tengo, Arturo Camacho, sí, tiene la mano levantada. Adelante, Arturo.
Hola Luis, muy
Hola.
interesante y muy espectaculares sus resultados. En realidad sí tenía una pregunta, pero creo que ya la respondiste durante la respuesta a la doctora Cecilia. Pero bueno, mi pregunta era cuál era el rol, porque el criterio para la formación de droplets y superfluidos nos lo bosquejaste como un análisis en términos de las dimensiones de la densidad, perdón, de que el campo medio escala, cómo escalaban las densidades, el término de campo medio y el término de la interacción. Mi pregunta era respecto al, ingenuamente, ¿no? Si uno hace solo campo medio, ¿no? Las interacciones, las densidades no entran en el criterio de colapso, simplemente es un cociente entre cuánto vale por ejemplo, en las mezclas que nos comentaste, cuánto vale la longitud de dispersión de las dos componentes con la interespecie.
Exacto.
Entonces, me llama un poco la atención que el criterio que nos presentaste solo sea en términos de densidades y que no esté ni en el término ni en el problema de una sola especie, ni en el problema de la mezcla, que no aparezcan las longitudes de dispersión, pero creo que fue lo que le comentaste a la doctora.
No es que no aparezcan, digamos, aparecen en los prefactores, digamos, por ejemplo, del Li-Yang aparece la longitud de scattering y juega un papel, definitivamente. Porque yo el punto que quería hacer ahí es más el hecho de que si fijo las scattering lengths, digamos, estoy fijando los prefactores, digamos, del mean field y del Li-Yang, y eso me está fijando cuál es la densidad crítica. Pero la densidad crítica depende de esos prefactores y depende de las scattering lengths. En el caso de mean field, la estabilidad no depende de la densidad porque todo escala con la densidad, digamos. Pero vamos, los prefactores, digamos, dependen de las scattering lengths, dependen de los dipolos, dependen de la situación. Sí, seguro. De hecho, depende en gran medida de cuál es la relación entre para dar la relación entre las dos interacciones.
Okay.
Muchas gracias.
Rubén Barrera.
Bueno, gracias por el coloquio. Fue muy interesante. Yo no me había metido mucho en estos sistemas. Mi pregunta es realmente una curiosidad nada más, un detalle. Cuando tratas de tomar los sistemas reales, modificas la interacción dipolar de una manera que creo debe tener en cuenta la estructura interna de los elementos que están interaccionando. Esa interacción, esa A que hay ahí, qué es lo que significa y qué tanto puede modificar porque debe haber una parte repulsiva, yo creo, cuando la S es muy pequeña. Entonces, ¿y qué tan importante eso es? Es una curiosidad.
De hecho, la S está aquí, en este caso, es siempre mayor que 1, digamos, es interacción porque es discreto, o sea, es 1, 2, 3, o sea, pero el A tiene una explicación física muy simple, y es el hecho de que si tengo puntos, como en este caso, digamos, se ven como puntos a cualquier distancia, de este vecino, al siguiente, al siguiente, al siguiente. Si tienen una cierta estructura transversal, cuando me acerco, digamos, estoy viendo que ahora ya no se interactúan como puntos, sino como nubes, digamos.
Sí.
Cuando están muy lejos de entre sí, cuando se van muy lejos, se ven como puntos, obviamente, y por eso esta interacción de aquí, cuando S es muy grande, va como 1 dividido por S al cubo, seguro. ¿Vale? Pero si cuando se van acercando, digamos, este A de aquí viene determinado, es una función de la relación entre esta dimensión y este spacing de aquí. Cuanto mayor es esta relación, más importante es esto. Y eso es porque ahora, en vez de verse como puntos, se ven como dos planos, digamos. Y ahora estoy integrando la interacción dipolar sobre el plano. Y eso ya no decae como la distancia al cubo.
¿Y esa A es un parámetro o es...?
Esa A es un parámetro que se controla con esta dimensión transversal. Y esto es importante para los experimentos porque típicamente va a tener que esta dirección transversal es típicamente, en muchos experimentos, significativamente más grande que esta dirección de aquí.
Ajá.
Y eso significa que este A va a jugar un papel relativamente importante. Y como digo, eso tiene consecuencias para la dinámica. Puede tener consecuencias para la dinámica porque si tú calculas solamente el vecino próximo y asumes que todo decae como 1 dividido por R al cubo, tienes una respuesta, pero la respuesta real es diferente.
Okay.
Puede ser significativamente diferente. Y puede ser el sistema mucho más, digamos, tender mucho más a localizarse.
Sí. Gracias.
Miguel Ángel Solís.
Hola Luis.
Hola.
Felicidades por la plática, digamos, se ve que es una gran cantidad de chamba, digamos, que están haciendo y varios grupos, muy interesante, ¿no? Qué bueno. Mira, cuando se pensó que se había descubierto la supersolidez, allá por el 2012, se hablaba, digamos, de que la supersolidez era, sobre todo, claro, se estaba mirando, digamos, en el helio 4, ¿no? Se miraba como que las vacancias en el helio 4, digamos, se empezaban a mover y de manera correlacionada, así entonces implicaba que los átomos, digamos, se movieran de igual forma, ¿no? O sea, sin embargo, bueno, se demostró posteriormente, digamos, de que ya no estaba sucediendo eso precisamente, ¿no? Sino habían descubierto otro tipo de fenómeno, ¿no? De rotación. Pero claro, ahí estamos hablando de átomos dentro de un arreglo periódico. De tu plática, lo que me queda, digamos, bueno, aparte de que me sorprendió, digamos, que Gross-Pitaevsky, digamos, sea suficiente, digamos, para escribir todo esto, ¿no? De tu plática me quedé con la idea de que están obteniendo, al menos desde el punto de vista experimental, estos condensados, pero que pueden, digamos, volverse bloques, ¿no? O sea, gotas, y que se arreglan, digamos, debido a las interacciones. Pero allí me queda como que no estoy logrando compaginar, digamos, esa idea de supersolidez, digamos, en el helio 4 y lo que estás mencionando dentro de este sistema de gotas, un arreglo periódico, ¿no? Allí podrías, digamos, comentar al respecto, digamos, entiendo, digamos, que en tu condensado al momento, digamos, de volverse gotas, ciertamente hay rompimiento de simetría traslacional, y tienes un superfluido, pero tienes conjuntos de superfluidos. Es como si me dijeras, ¿sabes qué? Yo lo podría mirar de otra manera también. Por ejemplo, tú tienes un superfluido, lo generaste, digamos, en Innsbruck, o lo generaste, digamos, en el MIT, o lo generaste, digamos, en cualquier otro lugar, y entonces tienes 3 fluidos. Y entonces dices, ya superfluidos, perdón, condensados. Entonces podrías decir, ya tengo un supersólido, digamos, pero con distancias enormes, ¿no? ¿Sí ves la pregunta?
Sí, veo la pregunta, pero es precisamente la diferencia entre lo que hablaba antes de tener un régimen en el cual las droplets son independientes con respecto de las demás. Ese es un régimen en el cual cada una de las droplets, por separado, forma un mini superfluido, digamos. De hecho, se puede estudiar la superfluidez de cada una de ellas por separado, estudiando, por ejemplo, por ejemplo, reducción del momento de inercia o este tipo de cosas en scissors mode, y de hecho se ha estudiado ya para droplets individuales. Ahora, la cuestión, y esta es la cuestión fundamental, es si las droplets tienen una relación entre ellas. Y eso no va a ocurrir si tengo una droplet en el MIT y la otra la tengo en Innsbruck, digamos. No van a hablar entre ellas. No tienen un phase link entre ellas. Y eso es crucial. Esto es como una especie como de Josephson Array. Digamos, es similar a una Josephson Array, aunque la física es realmente más compleja que eso porque se basa en el hecho de que hay una especie como de background particles en un halo, digamos, alrededor. Pero se parece a lo que tienes en una Josephson Array. Tienes una especie como de link, que sería como la Josephson Energy, digamos. Y la cuestión es si ese link es lo suficiente como para tener superfluidez. Definitivamente, lo que tienes en este tipo de sistemas es phase coherence. Eso es seguro. Eso es seguro porque eso se puede comprobar. Si fueran condensados individuales separados, no tendrías phase coherence. Y eso significa que si tienes dos, aunque no sean phase coherent, y haces interferencia entre ellos, vas a tener siempre interferencias. Eso no hay problema. El problema es que si tienes muchas de ellas y haces interferencia, la fase no está bien definida y por lo tanto tienes una mancha, digamos. Y esto es una manera de diferenciar. De hecho, en este tipo de experimentos, usando lo que se llama time of flight measurements, puedes diferenciar entre si tienes un sistema coherente de arrays o no. Y eso no queda duda, digamos, de los experimentos. Ahora, la otra cuestión es hasta qué punto es superfluido. Porque superfluido tienes que encontrar una serie de cosas muy determinadas para determinar, por ejemplo, si es superfluido. Una de ellas es la reducción del momento de inercia o la aparición de vórtices, por ejemplo, en este tipo de sistemas. Y esto, digamos, la gente ha estudiado, o por ejemplo, cómo son las excitaciones, si hay excitaciones asociadas con la superfluidez en el sentido de que tienes fonones, por ejemplo, asociados con la superfluidez. Eso se ha estudiado, por ejemplo, en arrays unidimensionales, pero en arrays bidimensionales es un problema mucho más complejo. Y ahora mismo es un problema, por ejemplo, que nosotros estamos estudiando cómo se podrían generar vórtices y todo esto, aunque no es tan sencillo como en un condensador normal en que puedes generar vórtices. Ahora, ¿cuál es la relación entre el supersolid de Andreev, por ejemplo, que la gente hablaba sobre vacations, por ejemplo, este tipo de cosas? Es que hay diferentes tipos de supersolid. No todos ellos están... Lo importante es cómo establezco la superfluidez. Una manera de establecer superfluidez es a través del movimiento de vacations en un cristal, digamos. Y eso, de hecho, se ha estudiado en sistemas parecidos a este, en sistemas de Rydberg, por ejemplo, por gente de Quantum Monte Carlo. Pero para eso necesitas un número de partículas muy, muy pequeño. O sea, tienes una especie como de droplets, pero con un número de partículas muy pequeños y puedes tener vacation supersolidity. Ahora, el problema, que es un problema añadido aquí, y es un problema importante en el caso de Rydberg, es que tienes también la temperatura en este sistema. Y sí, y pasa como en Josephson Array. Si el Josephson link, la energía asociada con el link es muy, muy pequeña, la temperatura puede llegar a destruir la superfluidez, por ejemplo. Y entonces eso significa que tienes que tener mucho cuidado de que el phase link sea lo suficientemente fuerte, ¿no? Es un problema complejo, pero como digo, el hecho de que sean coherentes y que hablen y que tengan un phase link, eso está bastante claro, digamos. O sea, son droplets que no son independientes con respecto de la otra. Es muy diferente que un gas de condensados separados.
Ok, bueno, abusando de nuestro anfitrión, nuestro conferencista, vamos a permitir una última pregunta. Eduardo Padilla.
Hola, buenas. Yo tengo una pregunta muy técnica. ¿Es posible tener, tus dímeros pueden ser fermión-fermión? no, de alguna forma no, las interacciones de tres cuerpos, pues me imagino que estarían de cierta forma no permitidas por Pauli. Entonces sí es posible tener ahí dímeros fermión-fermión del mismo isótopo, de cierta forma. Y la segunda pregunta es si se puede, ¿cómo cambian experimentalmente la densidad para alcanzar la densidad crítica? ¿Se aumenta el número de átomos o se cambia el volumen o cómo lo hacen?
Primero, la segunda es relativamente fácil porque lo que cambias es cuál es la densidad crítica. Puedes cambiarlo con la scattering length, por ejemplo, y eso te varía cuál es la densidad crítica, sin necesidad de cambiar el número de átomos. La primera pregunta no la he entendido muy bien, pero ¿estás hablando de dimers en el sentido de, por ejemplo, la discusión que he hablado en Optical Lattices o en qué sentido?
No, cuando tienes tu molécula, imaginemos, se pueden formar una molécula fermión-fermión.
Okay. Las moléculas pueden ser fermiónicas, o sea, puedes tener fermion boson, por ejemplo, si tienes bialkali molecules, por ejemplo, como potassium rubidium o sodium potassium, esto puedes hacer moléculas que sean fermiónicas, por ejemplo, sodium potassium fermiónico, y de hecho la gente lo ha hecho. Y puedes tener también moléculas bosónicas en las que, por ejemplo, tengas dos fermiones juntos. El problema de las moléculas bosónicas en particular, pero
Se congeló, ¿verdad?
Y parece que se bloqueó tantito.
¿He vuelto? Sí.
Sí, ya.
Sí.
Lo que digo es que puedes tener una colisión entre moléculas, por ejemplo, rubidium cesium o potassium rubidium. Entonces tienes una colisión que es exotérmica y eso te va a destruir el sistema. O puede suceder algo más sutil que eso, que es que tengas dos que no tienen una colisión exotérmica, no tienen una reacción a no ser que pongas energía, pero al colisionar entran en un hay como spin orbit coupling, forman una especie como de canal cerrado con muchos estados y es como entrar en una botella y tener que salir de ella por el mismo agujero. Y eso crea un complejo, que es lo que se llama sticky collisions, como si se quedaran pegadas, que también lleva a pérdidas importantes. Entonces, la manera de evitar que esto suceda es evitar que las partículas se vean cerca la una de la otra. Y esto es la idea del microwave, del shielding que he comentado antes. Porque sin esa idea, que ahora mismo se ha explorado ya, de hecho ha habido papers muy interesantes el año pasado en Gila, en Múnich y en varios otros sitios, sin eso no puedes tener un condensado de moléculas y no puedes tener un Hubbard model tampoco, porque puedes tener un spin model, pero no un Hubbard model en el que las moléculas se muevan. Porque si se mueven y se ven, entonces es el final.
Muchas gracias.
Ok, bueno, pues muchísimas gracias, profesor Santos, por su excelente e interesante charla y por la discusión, por todo este tiempo que continuó después de la conferencia. Los invito a todos a que le demos un aplauso al conferencista del día de hoy. Y esperemos que en un futuro no muy lejano puedas venir aquí a México y no solamente dar una charla, sino platicar con muchos de nosotros. Hay mucho interés en nuestro instituto sobre estos temas, como te habrás dado cuenta.
Perfecto. De hecho tengo un amigo mío muy bueno que está allí en el departamento de astronomía, de hecho.
Ok.
De la UNAM.
De la UNAM, sí, es universidad grande. Pues muchísimas gracias de nuevo y gracias a todos por asistir. A reserva de algún comentario adicional, damos por terminada la sesión el día de hoy. Muchas gracias.
Muchas gracias. Muchas gracias, Luis.
Gracias.
Y a
Muchas gracias.